Hi, my name is Justine Toel, and this is my MAE ECE 535 demo for inductive heating. The theory behind inductive heating is Faraday's law, which states that time-varying flux linkage induces voltage in conductors. In this case, I'm using a stationary coil with a time-varying magnetic field. The inductance of the coil can also be described using the formula for L. The rapidly alternating magnetic field in the primary coil generates eddy currents in an inserted object. Eddy currents are the result of Faraday's law. The eddy currents flowing through the resistance of the material causes it to heat through Joule heating. The effectiveness of induction heating on objects depends on several factors. It works on conductors and cannot directly heat non-conductors. Magnetic parts are easier to heat due to the combination of eddy currents and hysteresis that are present. The thickness of the object also has an effect. Thin parts are easier to heat due to higher surface area to volume ratio. Lastly, more resistive parts are quicker to heat. For this demo, I built and used a 0-voltage switching current to create the needed oscillating magnetic field. The significant components of a ZVS circuit are MOSFETs, diodes, capacitors, inductive chokes, and the primary coil used for the inductive heating. For this demo, I made several different versions of the ZVS circuit in order to experiment with parameters of capacitor size, voltage and current supply, and the heated object's thickness. On the left, you can see the circuit diagram for the ZVS circuit that I built. On the right, you can see all the different elements used for both the circuit and the objects that were heated. My first experiment was using circuit 1 to heat up an unfolded paperclip with a thickness of 0.8 millimeters. For all of these demos, I measured the time it took for the object to get red hot to have a consistent basis of comparison. When the circuit was connected without any object in the coil, the variable power supply was set to 10 volts and had a 2.8 amp current draw. When the paperclip was inserted, the current draw increased to 3.9 amps. The paperclip took 5 seconds to heat to a red-hot glow. Next, I used the improved circuit 2 to heat up an identical unfolded paperclip. The most significant change in this circuit was a larger capacitor array. When the circuit was connected without any object in the coil, the variable power supply was set to 10 volts and had a 5.1 amp current draw. When the paperclip was inserted, the current draw increased to 6.1 amps. This time the paperclip took only 3 seconds to heat to a red-hot glow, which is a 40% decrease in time. I then tried heating up a nail with this configuration. After waiting 91 seconds, it was hot but still not red hot, and I had to abort due to overheating of the circuit itself. Lastly, I connected circuit 2 to a 24 volt 15 amp power supply. I inserted an identical nail to the last experiment, and it now heated to a red hot glow in only 7 seconds, which was a greater than 91% improvement. This improvement in performance was a result of the increased current flow through the coil, which caused a stronger magnetic field. The results from all of the experiments are detailed in this table. 2 final experiments were chosen to demonstrate 2 things: the rapidness of the temperature increase using a kitchen thermometer and the effect of heating non-magnetic and non-conductive materials. When a cooking thermometer was inserted into the coil, it heated up by 300 degrees in only 2 seconds. Lastly, I put some heat shrink on a piece of bare copper wire. The heat shrink is non-conductive and the copper wire is non-magnetic. When this object was inserted, it took longer to heat than the thicker steel nail that was tried before, but the copper wire did heat up enough to activate the heat shrink. This demonstrated both the effect of using magnetic versus non-magnetic materials and also a method that could be used to heat up a plastic material with an induction coil. Thank you for watching my demo.